Hello, good evening, students. How are you, all of you? I hope all of you are doing well. You are studying, you are enjoying your life, right? So, we have to study something, right? So, we are studying about the chapter hydrocarbons. So, we have studied about alkanes in the last class. I hope you remember all the points that we have discussed in the last class. So, today we will continue that. So, we are studying about organic chemistry. It is a continuous process from GOC, IUPAC nomenclature onwards. We are studying. So, next year also, you will study this. It's a never ending process, right? So hydrocarbon, that is our chapter, is very important. Why? These are the basic things. Next year, if your basics are clear, then it will be very easy for you, right? So first of all, I'm launching the technical check here. If there are any issues with my audio, video, or any network issues, you can let me know. We will sort it out and we will start the class, right? Okay, you two friends, hi, good evening. So YouTube friends, you can give me the answers. I will ask you some questions. The questions are very, very important. So for those questions, you can give me the answer in the live chat. Okay, you have to use everything. Technical things, you have to use that. Okay, so technically, I hope everything is perfect. If everything is perfect, without wasting time, let's jump into our topics. So what are the topics that we are going to study today? First, we will study about chemical property of alkane. What is alkane? CC, single bond, right? Then conformation. That's a new thing for you. Conformation. We will study about conformation. What do you mean by this conformation? Then alkanes, next one. This chapter, alkanes, alkenes. Then alkynes, triple bond. Then last there is benzene, aromaticity, etc. We will study about that also. Then we will study about preparation, or I can say methods of preparation of alkenes. We already studied how to prepare alkane, right? So these are the topics that we are going to study today. So let us start it. So before starting today's topic, what we have studied in the last class. So we have to recall the things, right? So last class, it was all about alkanes. So alkanes, colorless, odorless, then immiscible in water. Why? Non-polar, like dissolves like. So water is polar in nature. Then boiling point increases with increase in molecular mass. Then what is the relation between boiling point and surface area? That is directly proportional, right? Then surface area decreases, boiling point also decreases. That we have studied. Then generally they are inert alkanes, but under special condition, they will undergo some reaction. Then we have studied halogenation. What is halogenation? It is a substitution reaction. Like in football, Lionel Messi is coming in, then Diego Maradona is coming out, is going out. So that is a substitution reaction. We have studied about that also. Then in that substitution, small topic that is halogenation, but is very important. So we have an alkane, then we have halogen. X2 means halo, X means halogen, can be Cl2, Br2, etc. In the presence of sunlight, H2 means in the presence of sunlight. What we have to do? Just remove one hydrogen from alkane, add halogen in that place. Substitution. Hydrogen is getting substituted by our halogen, right? So alkane to haloalkane, that is halogenation. Then combustion reaction we have studied. That is complete combustion reaction with oxygen. Then how to balance the equation is a simple trick for you. You have to use that. What are the products obtained? Carbon dioxide and water. You know, from lower classes onwards, so you are studying about the products. Carbon dioxide and water is formed by the combustion of hydrocarbon. That's it. So these are the things that we have studied in the last class. So recap is done. So what is next? So we have to do a question based on this one. This is from NEET, a previous year question. First, read the question carefully. Then after that, read the options. Then eliminate some of the options. Then take the correct one, right? So what is the question here? The alkane that gives only one monochloro product. That is only one chlorine. We have to remove one hydrogen, add one chlorine. On chlorination with Cl2, halogenation here, chlorine is getting added, substitution, right? Cl2 in the presence of diffuse sunlight. So H nu is present. So let us try it out. We have 2,2-dimethyl butane. So let us write the structure. So you have to do that. You have to do along with me. So I will give you some hints for you. So first try to write the structure. 2,2-dimethyl butane. So what is that? So I'm drawing 1, 2, 3, 4. 2, 2. This is 1, 2, 3, 4. Then one methyl group here, one methyl group here, second carbon, right? Then neopentane, what is that? Neopentane. Neopentane means one carbon should be quaternary. So I'm writing it as carbon, then C, C, C. Okay, now it's a tertiary carbon. This one is tertiary. So I can write it like this, neopentane. So CH3, then CH3, then CH3. That is our B option. So what is normal pentane? So 1, 2, 3, 4, 5. That is normal pentane. What is isopentane? There should be one carbon atom. That should be tertiary in nature. So let us write that carbon, then CH3, CH3, then one more CH3, then one more carbon. So this is a tertiary carbon, right? So now 1, 2, 3. So one hydrogen should be present. So 3 isopentane, right? So CH2, then CH3, right? So that is it. So we need only one monochloro product. If the hydrogen, all the hydrogen present in this equivalent, then we will get only one product. So let us start from here. So let us start from here, carbon, then H3. So what about this carbon? That is primary. So primary hydrogen. So this is also primary hydrogen. This is also primary hydrogen. This is also primary hydrogen. How? This is a primary carbon. Why? That carbon is attached to one carbon atom, primary carbon. Then hydrogen present there, that is known as a primary hydrogen. All these 9 hydrogen atoms are equivalent in nature. Suppose I am removing one hydrogen from here, adding chlorine. So I will get CH2Cl. If I'm removing one hydrogen from here and adding Cl, CH2Cl, from here also I can remove, from here also I can remove. So from wherever I remove, I will get the same product. You can write the IUPAC name of the product. So all the hydrogen atoms are equivalent. So by chlorination, I will get only one monochloro product. So what about this one? This one, this is CH3, CH3, then here CH3, then CH2, CH3, then carbon is present, right? So this is primary hydrogen. This is a secondary hydrogen. So different hydrogens are present. So if I remove one hydrogen from here and replace it by chlorine, I will get one product. Suppose I'm removing one hydrogen from here and replacing it with chlorine, then the name of the product will be different. So what about the second case, B option? All the hydrogen atoms are equivalent. From wherever I remove hydrogen and add chlorine, I will get the same product. Actually, this is substitution reaction. What about this one? Here we have CH3, here CH2. So this is primary hydrogen. This is our secondary hydrogen. Not equivalent, they are different. So this is secondary hydrogen. This is a primary hydrogen. So I will get different products. Okay, not a single product. So what is the correct answer? Which one is the correct answer for you? That is our neopentane. So that is it. We have studied how to write the structure in IUPAC nomenclature, that area, GOC class, right? So you have to use all these things here also. So we have solved a previous year question, NEET previous year question. So it is very important to solve previous year questions also. We have done that, right? So 4 marks guaranteed. So we got the answer. So that is all about the recall question. Then, so now let us start today's topic. So we are studying about alkanes, some chemical properties. What are the reactions shown by alkanes? Now we are going to study about pyrolysis. What is pyrolysis? Pyro, that means temperature. So temperature is high. Lysis, we are breaking the bond. So at high temperature, some bonds are getting broken. That is pyrolysis. Or I can say cracking. I'm cracking a higher hydrocarbon at high temperature, right? Then small fragments will be formed. That is known as pyrolysis. A small example for you. I have C6H14. What is that? Alkane or alkene? Of course, that is an alkane, right? So we have hexane here. We have hexane here, or I can say normal hexane, right? Then at high temperature, the bonds are getting broken. Then different products, different small fragments will be obtained. So there are different possibilities. Let us check some of the possibilities. From C6H14, C6H12 is formed. So what is remaining? So what is the difference between these two? That is hydrogen, H2. So plus H2. So small fragments, hexane to hexene, small fragments are formed. C6H12 plus H2. Then another chance, it can be C4H8, right? C4H8 can be formed. Then what is remaining? So C2H6. Small fragments are formed at high temperature, right? Then C3H6, we have C3H6. Then what is remaining? C3H8. So by applying high temperature, this higher hydrocarbons are getting broken. Okay, small fragments are formed from. So that is known as pyrolysis or cracking. Only at high temperature, 773 Kelvin means so temperature is very high. We can't imagine that, right? So that's about pyrolysis. Very simple example, simple reaction of our alkane. So let us start. Let us study about the next one, right? Then one small point, pyrolysis of alkanes is believed, okay, it is believed to be a free radical reaction. You know what is free radical? So intermediate free radical is formed, right? So it is believed, okay, no need to study about the mechanism. What is mechanism? So what are the steps involved in the reaction? Product is formed from the reactant. In between, there are so many steps. Maybe some intermediates are formed. That is what we call as a reaction mechanism, right? Then this is very important for you. Conformations, a very new topic for you. What do you mean by this conformations? Let us find it out. What is conformation? First, read the definition. Spatial arrangement. So in the 3D space, the arrangement of atoms are different, right? Which can be converted, spatial arrangement of atoms, which can be converted into one another by rotation around a CC single bond. So alkanes, we have alkanes, right? So alkanes, head-on overlapping. So free rotation is possible around that sigma bond. So if I rotate that, different arrangement will be possible for the atoms. Those things are known as conformational isomers. There is no change for the molecular formula. Only spatial arrangement of the atoms is getting changed. So that is known as conformational isomers or conformers. Or I can also call it as rotating. I'm rotating, right? They are also known as rotational isomers or rotamers. So conformers or rotamers. So we are changing the spatial arrangement of atoms. How it is possible? It is a sigma bond. Free rotation is possible around our sigma bond, right? So maybe we have some sort of confusion. So I have a simple example for you. So what is this? This is our CH3, a CH3 single bond CH3. It is a sigma bond. So free rotation that is possible. Then this is our methyl. Assume it as methyl. Okay, it is actually methyl group. This one, blue color, that is carbon. So this is our second carbon. So carbon sigma bond is present. What about this white ball? That is hydrogen. So first hydrogen, second hydrogen, third hydrogen. Then this is front side. Suppose imagine it as front side. Then here we have back side. That is 3 hydrogen atoms are attached over a carbon. So that is the point. So for CH3 group, I'm keeping it as fixed. Then the behind, rear, back side carbon and 3 hydrogen attached to that carbon. So I'm rotating it along the carbon-carbon bond. So I'm rotating. So here it is fixed. So the backside carbon, I'm rotating this one, I'm rotating, okay. Then if I rotate, then different arrangements are possible. So initially, this is our carbon-hydrogen bond. Backside also, there is carbon-hydrogen bond. So I'm rotating. Now, it is different. The arrangement of these atoms, it is different, right? So that is known as conformations or conformers or rotamers, okay? So let us study about this conformation in detail. So how to do that? So what is happening here? So we have ethane, CH3. So first CH3 group, I'm keeping it fixed. Then the backside CH3, I'm rotating that one. If I rotate that one, different spatial arrangements are possible. Okay. Then this is the same thing. Then how many possible arrangements are there? I'm rotating this one. Okay. So initially, this is carbon-hydrogen bond, front side carbon. This is also carbon-hydrogen bond. So I'm rotating 1 degree, then one arrangement. I'm rotating 2 degree, another arrangement. Then 3, 4, 5, 6, 7, 8, 9, 10. There are infinite number of arrangements possible. Okay, I can rotate it by a different angles, 1 degree, 2 degree, 3 degree, etc., etc., etc. So how many conformations, how many conformers are there for ethane? It is infinite number. There are a lot of conformers possible or rotamers possible for our small ethane, right? Sir, how can we study about all these conformers? It is not possible for us, right? So we have to study about the important conformers. So which are the important conformers, right? So what is the answer for this question? Possible number of conformers of ethane, that is infinite number. There are a lot of rotamers possible for ethane, but we are going to study about two extreme cases. So what are those extreme cases? So first one, that is eclipse conformation. You might have heard about lunar eclipse. So what is that? So one is staying behind, okay? Then, or staggered conformation. These are two extreme cases. One is eclipse conformation, eclipse, lunar eclipse. You have to remember that one. Then staggered conformation, right? So let's study about this eclipse conformation and staggered conformation. So how to study about this one? So we have a Sohos representation. How to represent ethane, how to show eclipse conformation, how to show staggered conformation. So let us study about Sohos representation of ethane, or we can call it as Sohos projection. So you can see it here. So yeah, there is a carbon-carbon single bond. That's a straight line, right? Then carbon and some lines you can see. Carbon is present here. This is our hydrogen. This is our hydrogen. This is hydrogen. So no need to write the hydrogen. Just show a line. So you have to understand that is our carbon-hydrogen bond. So I can say this is a friend side carbon, friend side carbon. Okay, this is a friend side carbon. What about this one? If it is friend, that is a back. So I can say a back side or rear carbon, rear carbon, rear carbon. What about this line? So that line indicates carbon hydrogen bond. Okay, so there is a carbon carbon bond, then carbon hydrogen bond. It's a straight line. It is somewhat tilted. Okay, so that is Sohos. A Sohos projection is a view of a molecule down a particular carbon-carbon bond, CH3, CH3, let's say carbon-carbon bond. So along that bond, we are viewing the molecule, right? Then why Sohos? Eclipse conformation, we have to first study. So what is the eclipse conformation? Eclipse conformation looks like a carpenter Sohos. So what you can see here? Here we have a hydrogen. Here we have a hydrogen. Just behind that, there is one more hydrogen. So here one, just behind eclipse, eclipse. If I look at this one, okay, I can see only one hydrogen. There is one more hydrogen behind that one. It is eclipse. Okay. So eclipse conformation looks like a carpenter's Sohos. So this is carpenter's Sohos. You might have seen this if you have went to some carpenter's house or some carpentry works are done in your house. You might have seen this one. So one hydrogen, it is just behind the other. Then the next one, then just behind the other. Then the third one, just behind the other one. So this is known as Sohos, carpenter's Sohos. So that is about eclipse conformation, right? So the molecule is viewed along the molecular axis. So this is about our eclipse conformation. There is a front side carbon, there is a back side or rear carbon. Then 3 carbon hydrogen bond, front side, 3 carbon hydrogen bond, back side. So they are eclipse, right? So that is our Sohos projection. So Sohos projection of ethane. This is our front side carbon, then 3 carbon hydrogen bond. So this is our back side carbon. So they are just behind each one, right? Eclipse. So that is it. That is our Sohos projection of ethane. So this is a representation. Eclipse conformation of ethane. Okay. Next one, staggered conformation. So initially this hydrogen and this hydrogen, they are eclipse, right? Then after that, I'm rotating. Now you can see this hydrogen is standing like this. So I can show here. Here we have the first hydrogen, carbon hydrogen bond. So CH3 group, front side CH3 group, that is fixed. Back side only I'm rotating, right? So initially this hydrogen, this carbon hydrogen bond is present like this. I'm rotating that one, rotating that one. Now it is down. It is pointing downwards. So this is our carbon hydrogen bond, this one. So initially this bond and this one, they are eclipse, right? Now this is the first one. This is another one. So one is pointing upwards, one is pointing downwards. It is not eclipse. It is far away from each other. Initially, they were just behind. They were very close. Their electron cloud were very close. So electron cloud close means repulsion. There is high chance for repulsion. What about staggered conformation of ethane? This carbon, hydrogen, they are far away from each other. Far away from each other means the repulsion of the electron cloud, that is also very less. Okay, so this is eclipse, this is staggered. So which one will be more stable? We will study about that. And you may have a doubt. So what is that? In between, I can rotate it 1 degree, 2 degree, 3 degree, 4 degree, etc. In between, you can find so many conformers. Is there any name for those conformers? Of course, there is a name. In between, there are so many conformers. We can call it as skew conformers, skew conformers. So we are not going to study about that. So we need to study about eclipsed and staggered conformations only. Then first one is Soho's projection. Soho's explained a way how to study about the conformation of ethane. Next one, Newman came. So Newman proposed a projection or representation of ethane. So now we are going to study about Newman projection of ethane. So molecule is viewed as the CC bond head-on. So what is that? We will explain. I will explain to you. Okay. So here some structures are there. Let them come to the screen. Okay. Here, this is our front side carbon. This dot, that is the front side carbon. This circle you can see that is our back side, rear carbon. Okay. Then here you can see observe this one. This is a front side carbon. Then hydrogen atoms are attached. Carbon hydrogen bond is present. CH, 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 right? Then back side, that is our circle that is the rear carbon. To that carbon, 3 CH bonds are present. So this is hydrogen number 1, hydrogen number 2, hydrogen number 3. Now you can see this hydrogen and this hydrogen, they are eclipse, right? They are just behind one another. Okay, so I can say this is eclipse conformation. This is our eclipse. Okay, so that is our eclipse conformation. Okay, Sudhar Suhani, welcome to the class. The next one is staggered conformation. So staggered conformation. So this is our front side carbon. Then we have 3 carbon hydrogen bonds present here. So carbon hydrogen bond. So you can see 3 carbon hydrogen bond. So here carbon hydrogen, then backside carbon hydrogen. They are far away from each other. So what about repulsion? Repulsion is very, very low. So I can say minimum repulsion. If repulsion is minimum, stability will be high. We have studied that. So this is our front side carbon and 3 carbon hydrogen bond. So the circle, that is our rear carbon and carbon hydrogen bond is present, right? Okay, that's about Newman projection. So we have studied Newman projection formula, then Soho's projection of ethane. So these are the examples for you. You can identify from here eclipse. This is our staggered. Which one is more stable? You know that. Okay, so let us study about some more. I have already explained carbon hydrogen bond in the front side carbon, then carbon hydrogen bond in the back side carbon. In the eclipse conformation, they are close to each other, right? It is like your brother and sister in your house. Maybe this is me and this is my sister. If they're close to each other, then always fight. So what will your mother do? She will try to separate you. So she will ask you to go to this room and study, then brother go to this room and study, like that. So we have to keep it far away from each other, then only less fight. Less fight means your mother will be in a peaceful state, right? There will be no tension. There will be no strain for your mother. Similarly, here also, this front side carbon, carbon hydrogen, then back side carbon, hydrogen bond. They're close to each other. Electron cloud is there, like you and your sister, you brother, right? So repulsion is very high. So repulsion very high means stability is very low. What about energy? Energy is very high. You and your sister, the energy will be very high always, right? Then staggered conformation, I have a front side carbon, carbon hydrogen, then rear carbon, carbon hydrogen bond. They are far away from each other. They are in different groups. So peaceful state for your mother. So same here also. So minimum repulsion, minimum fight between you and your sister. So minimum repulsion means strain for your mother, that is very less. What about stability? Whole stability of your house, the stability will be high. Okay, so minimum repulsion, then minimum energy. Stability, that is very high for a staggered. So this is a previous year question. We have eclipse conformation, we have staggered conformation. So which one is more stable? Which one has less energy? Which one has more repulsion? Okay, so you have to study like this one, you and your sister. Eclipse, they are close to each other, more fight. maximum repulsion, then stability is very low, always tension for your mother, right? So that is all about eclipsed and staggered conformation. Then we are rotating this one. Okay, then carbon-carbon bond is present, carbon-hydrogen bond is present. Is there any change for the carbon-hydrogen bond length? No, there is no change. We are not changing the bond length. What about bond angle? We are not changing the bond angle. Okay, so in conformers, we are not changing the bond length. We are not changing the bond length and bond angle. That is also a very important point. So a question for you. So we have done with the theory. So you have to answer. Sutar Suhani can answer me. This is a question from NEET 2017. So read the question, then go through the options, then select the correct one. So with respect to conformers of ethane, which of the following statements is true? So bond angle changes, but bond length remains same. Bond angle and bond length both changes. Both bond angle and bond length remain same. Bond angle remains same, but bond length changes. So which is the correct answer here? You two friends, you can give me the correct answer in the chat, live chat. Okay. So I have just mentioned the point. You have to just remember that one and take the correct answer. 4 marks guaranteed. NEET question. Okay. So what is the correct answer? So without wasting any time, you can give me the correct answer. So I already mentioned both bond angle and bond length remain same. There is no change for bond length and a bond angle. So our C is the correct option for us, right? I hope this is clear to you. We are not changing the bond angle and bond length. So we have solved a question. So 4 marks, we are getting 4 marks from this point. So it's very important to solve the previous year questions, right? Now, our alkanes, it is almost completed. I'm not saying it is completed. Why? Next year also, you will study about the methods of preparation of alkane. How can we prepare alkanes? There are different methods. But next year, there should be something left for the next year also. So you can study those things later. So we have studied ample amount of examples. It is enough for your 11th class. Now, alkanes, that is completed. Then what is the second part? That is our alkenes. So what do you mean by this alkenes? So alkene means, you know, there is a double bond present, right? So carbon-carbon double bond is present. There is a multiple bond. So first bond, that is our sigma bond. Then next one, that is our pi bond present. We have studied this in chemical bonding chapter. So unsaturated open chain hydrocarbons. Okay, they're also known as another name for alkenes, that is olefins. Why they are known as olefins? Is there any reason for that? Yes, that is they are oil forming compounds. That is why they are known as olefins. So this is all about alkenes. Very simple, single things, right? So what is the general formula? I can write it as CnH2n. Then first member, what is that? C2H4. Sir, what about N is equal to 1? So that is not stable. So C2H4, that is the simplest member. First member, I can say like that. Okay, so it's about the alkenes. So let us study about the bonding. We have already studied. There is a carbon-carbon sigma bond. It is formed by the head-on overlapping, right? So sigma bond, hybridized orbitals are present. Then pi bond, p orbitals are forming pi bond by the lateral overlapping. Sigma bond, free rotation is possible around the sigma bond. So what about pi bond? So pi bonds are like this one. If I try to rotate this one, then they will be 90-degree. Then I have to break the bond. So the rotation around the pi bond, it is restricted. So we can say there is restricted rotation. Sigma bond, it is free rotation, right? So that is introduction of alkenes, double bond, sigma bond, then pi bond. It is formed with the lateral overlapping, right? So let us study about more things. The double bond in alkenes consists of one strong CC sigma bond. CC sigma bond, that is very strong. If it is very strong, how to break that? So we have to spend more amount of energy, or I can say bond dissociation enthalpy or bond enthalpy for a sigma bond is very high. So what about pi bond? Pi bond is somewhat big. Why? Lateral overlapping or sidewise overlapping only. So how to break that bond? So to break that bond, we have to spend less amount of energy. So I can say 284 kilojoule per mole. Then one more point. So due to the presence of pi bond, alkenes are more reactive than alkanes. Why? We have studied pi bond. There is a plane, then electron cloud are present above and below that. So a thief is coming. So this electron or money, it is clearly visible. So the thief can identify a lot of money in this house. Of course, he will attack. Similarly, this alkenes, electron cloud, pi electron cloud is visible to other people. So they will come and attack. So who is a thief here? That is E plus electrophiles. What is electrophiles? They're electron loving. They want some money. So money is visible in this house. Of course, they will come and attack you. So electrophiles are ready to attack these alkenes due to the presence of pi bond. What about alkenes? They are not showing off. They are not showing that we have money, lot of money. Come here, you can attack. It's not like that. Okay. So in the case of alkenes, this pi electron, the presence of pi electron, this attacking. Who is the attacker? That is electrophiles are coming and attacking. So reactions will happen. So compared to alkenes, double bond, pi electrons, it is more reactive in nature. So you have to remember this one. Okay, structure of double bond in alkenes. Then nomenclature of alkenes. We have already studied the complete IUPAC nomenclature. Is it required to study all these things again? So just as a revision, I will give you some example. You have to give me the correct answer in the chat. Okay, so nomenclature. So usually suffix "-ene" is used. What about alkanes? We will use "-ane", right? Then alkynes, we will use "-ine". So these are the common suffix. Then how to do the nomenclature, how to name a newborn baby. So select the longest chain containing double bond. So that double bond should be included. Try to include that double bond in the longest chain. Then double bond, it should get the lowest possible number. So we have studied about all these rules. Example, how to name this one? Then identify the longest carbon chain. Then double bond should be included in that. Then start numbering. Double bond should get lowest possible number. So what is the position of double bond? That is in the first. That is a position of our double bond. So these are the different examples. Can you name them? So I will give you 20 seconds. Within 20 seconds, you have to give me the correct answer. Right, nomenclature of alkenes. So what is the name for the first alkene? What is the name for the second one? What is the name for the third one? You have to give me the correct answer here. So what is it? How to name that? So first one, prop 1e, or if double bond is present at the first carbon, then we can directly write it as propene, right? Then what about the second alkene? Again, double bond, first carbon, first position. So how many carbon atoms in the longest carbon chain? 4 carbon atom. So that is bute, right? So what is the name? Bute 1e. Then what about this third one? You can see there are 2 double bonds present. 2 double bonds. You have to use di. Then how many carbon atoms in the parent chain? There are 4 carbon atoms. So what is the word root? That is bute. So what is the name for this one? A bute 1,3-diene. Is that correct? No, we have studied if there are 2 double bonds, then we have to end it with buta. So buta 1,3-diene, that is a name of the third alkene. Right? This is a very simple example. We have done so many complex example in the IUPAC nomenclature, right? So propanine, butene, buta, there is A, okay, not but, buta 1,3-diene. These are the examples for you. I hope no need of doing so many examples right now. We have already done that. So let us find out some new topics. Isomerism in alkenes. Again, if you have studied this IUPAC nomenclature, general organic chemistry, this will be very easy for you. Otherwise, maybe somewhat difficult. You have to study this. So isomerism in alkenes, Sanjeev sir taught you, right? Isomerism. Let us check it out. How many isomers are possible? What are the different kinds of isomerism, right? So we have alkene. So alkene can show structural isomerism, also geometrical isomerism, right? So free rotation is not possible in the case of alkene. In the case of alkene, sigma bond free rotation. In the case of alkene, a restricted rotation is possible. Then what about structural isomerism? There are different kinds of structural isomerism. Which are they? Do you remember those things? So first one, chain isomerism. Second one, position isomerism. Third one, functional isomerism, right? Then geometrical isomerism, cis trans isomers are the. So these are the different isomers, isomerism. The phenomenon is known as isomerism, right? So we have to check some examples. We have already studied. That is why I'm not stressing it too much. structural isomerism in alkenes. So first you have to draw all the possible structural isomers of C4H8. What is C4H8? That is but1ene or butene. So how to draw that? You have already studied. So I will directly give you the example. So first one, here the position of double bond first. Then what about the but1ene? The name is but1ene. Second one, the position of double bond, that is a change. So I can say they are position isomers, right? Position of double bond is getting changed. So here the double bond is present at the second carbon. So how many carbon atoms are present in the longest carbon? That is 4. So I can write it as but2ene. So but1ene, but2ene. What is the difference? Position of double bond. Then third one. So I'm getting some branches here. The position of double bond, that is first. Then the second carbon, there is a branch, CH3 is present. So it is different. The chain or skeleton, that is different here. So I can say 1 and C, A and C, they are chain isomers, right? So skeleton is getting changed. Then B and C, also the skeleton is changed, but molecular formula, that is same. So they are chain isomers. I can also, so IUPAC nomenclature, it is a 2-methyl prop1E. Then we have CnH2n. That's a general formula for alkenes as well as cycloalkenes. So what is the general formula? CnH2n. This is for alkenes. Then one more guy, that is our cycloalkane. Cycloalkanes, right? So C4H8, what is that? That is our cyclobutane. So here we have cyclobutane. Then any other cyclo or closed chain compounds present? Yes, of course. We can take cyclopropane. Then one CH3 there. Then what is that? In the first position, there is methyl group, like a branch. 1-methyl cyclopropane. So these are the different possible structures for our C4H8, right? So chain isomers, position isomers, etc. We have already studied about this. So no need to again study about all these things. It will take our time, lot of time, right? So geometrical isomerism, we will study about geometrical isomerism. It is more important here. So why geometrical isomerism in alkenes? There is restricted rotation around the double bond. This sentence, that is very important. So cis isomer and trans isomer is present. So what do you mean by this cis isomer? So the double bond is present. Here CH3 group, here also CH3 group. So same group, that is CH3. It is present in the same side of the double bond. What about this hydrogen? Yeah, hydrogen and hydrogen, they are present in the same side. So one above, one below. You can think like that, right? Then next one, that is cis. What about trans? Trans means opposite side, right? How to name this one? That is 1, 2, 3, 4. Second position, there is a double bond. So I can say but2ene. Then CH3 and CH3 in the same side of double bond. So I can call it as cis but2ene. How to name this one? That is 1, 2, 3, 4. That is 4 carbon atoms in the parent chain. That is but. Then position of double bond. Second, but2ene. So what is the difference? This is trans but2ene. First one is cis but2ene, right? So trans but2ene means here I have CH3. Then this CH3 is present in the opposite side. So that is trans. This is cis trans isomerism. That is our geometrical isomerism, right? Then cis isomers are more polar than trans. Why it is more polar? We have studied this in chemical bonding chapter. So look at here. This is carbon, that is sp2 hybridized carbon atom, and one CH3 group is attached there. I can say this as delta plus, and this sp2 hybridized carbon more electronegative. So delta minus. So what about the direction of dipole? That is positive to a negative. Should be pointing towards a more electronegative atom. So this is happening here, right? So the direction of dipole, same side, direction of dipole, carbon hydrogen bond. So we are saying that we are assuming that electronegativity difference between carbon and hydrogen is approximately 0. So no need to show the dipole there, right? Then what about trans? So trans, the CH3 group are present in the opposite side. So delta plus to minus, delta plus to delta minus. This is a direction of dipole. So what about this side? This is from CH3 group to sp2 hybridized carbon atom. So delta plus to delta minus. Look at the direction. They are in opposite directions. Somewhat they will get cancelled. So what about the polarity, right? So in the case of cis, so polarity is very high. The CH3 group are present the same side. So delta plus delta plus. Then what about trans? CH3 group in the opposite side. So dipole moment will get cancelled. Somewhat it will get cancelled. So dipole moment is less for trans. For cis, it is very high. It is polar in nature. So that is our cis trans isomers, right? So let us check some more example. So some more facts about our trans isomer and cis isomer. Cis butadiene, trans 2-butene. For solids, melting point of trans isomer is greater than cis isomer. So what is the reason for that? So reason for that is this trans isomer, right? So if I let us take the example, if I move from this side, so I am the person, I'm moving towards this side, symmetrical in nature. To this side, it is more symmetrical. So trans is more symmetrical in nature. So that is why the melting point of trans isomer is greater than cis isomer, right? So for solids, melting point of trans isomer is greater than cis isomer. So reason is greater packing efficiency due to more symmetry. It is more symmetrical in nature. What about boiling point? So boiling point is different. So boiling point of cis isomer is greater than our trans isomer. So what is the reason for that? Cis isomer is more polar than trans isomer. Polarity is developed. So high boiling point is very high for cis isomer. So boiling point of cis isomer is greater than a trans isomer. So these are the points regarding cis and trans. Okay, cis isomer, trans isomer. Trans isomer is more symmetrical in nature. Then cis isomer, it has more polarity. Okay, that is all about cis and trans isomers here. Now, we have to check the preparation. How to prepare these alkenes. There are different possible methods. So let us study some of the possible methods of preparation of alkenes. So let us start it out, right? Oh, who is this? Our Rocky Bai is here. So what is alkynes? Alkyne means the triple bond is present, triple bond, right? So what is happening here? So I'm taking alkynes on partial reduction. Reduction, that means addition of hydrogen, right? So alkynes on partial reduction with calculated. So I have calculation, okay? Calculated amount of H2 produces alkenes. Sir, we have seen this somewhere. Where? Yeah, alkenes to alkanes. Addition of hydrogen reduction. We have already studied that. Syn addition is possible. So here, what is happening here? So let us check it out. A catalyst, suitable catalyst is needed. So what is the catalyst used here? So I am using Lindlar's catalyst. What is Lindlar's catalyst? You have to keep it in mind. Lindlar's catalyst means palladium. So palladized charcoal, partially deactivated. Okay. So I want to limit the reaction. So I'm deactivating. How to deactivate that? Use some poison. So which are the poisons used? I can use sulfur. I can use quinoline. These compounds I can use, they will act like a poison. It will deactivate our palladized charcoal. Okay, so Lindlar's catalyst means palladium. Palladium in the presence of charcoal, then some poisons are used. Then also I can use palladium in the presence of BaSO4. That is also good for this reaction, right? So we have to break some bond and add hydrogen. So like the Rocky Bai. So Rocky Bai is breaking the bonds, right? Similarly, he has a tool, that is a hammer. So we a tool here, hydrogen is a tool here. So using hydrogen, we are breaking the pi bond. So let us take an example here. I have an alkane. So alkane, you can see here triple bond. So using this hammer, I have to break the double bond. Not double bond, a pi bond. Okay. So I'm breaking this a pi bond. Then I have to add hydrogen. How to add hydrogen? To the same side or opposite side? Here, I'm adding hydrogen to the same side itself. Okay, so palladium bar carbon means charcoal. So palladized charcoal in the presence of poisons. I'm adding hydrogen. That is reduction. Addition of hydrogen, that is known as reduction, right? So what is the product obtained here? So product is alkene. Cis alkene or trans alkene? Cis alkene means I'm adding two hydrogen to the same side. So look at here. Here R and R dash, that is our alkyl group. They are present in the one side. What about hydrogen? They are present in the opposite, not opposite, hydrogen in the same side. So we can call it a cis alkene. You can name it, suppose R is CH3. You can name it as a butadiene, cis butadiene. We have studied. So hydrogen, that is our hammer. Using that, we are breaking the pi bond. We are adding hydrogen to the same side. Like your syn addition, we have studied that. So in the presence of Lindlar's catalyst, cis alkene is formed. Sir, what about transalkene? Is there any method to form transalkene? Of course, there are methods. We will study about those methods later. Okay, so you have to remember what is Lindlar's catalyst. What about the addition to the same side or opposite side? Same side. So cis alkene, that is a product obtained here. Then some poisons are used to limit the reaction. Otherwise, the reaction will continue. We don't want that one. So that is why we are using some poisons also. Right? Then another question for you. Again, previous year question for you. Very simple. We have studied the concept. Just after that, a question for you. The most suitable, first read the question, then go through the options, observe it carefully, then tick the correct one. Or let me know the correct answer in the chat box, right? So read it. The most suitable reagent for the following conversion. So I have an alkyne. So alkyne is present. So alkyne is present. So we have to fill in the blanks. So what is used here? So cis-2-butene or cis-butadiene is used. Cis product is obtained. For cis-alkene, which reagent I have to use? Is this one? No. This one, yeah, H2, palladium, charcoal, then poison, quinoline. So this is the correct answer for you. So what about sodium in liquid ammonia? We will study about that. So next is all about sodium in liquid ammonia. Okay, so that will give transalkene. Actually, this will give a transalkene. So we will study about the mechanism, how transalkene is formed if we use sodium in liquid ammonia. Okay, I hope you have already solved NEET 2019 question. So we got 4 marks. So this 4 marks, it is very important in competitive exams, especially NEET exam. Okay, so if it is clear, so let us study about the next one. So what is next one? So what is the next one? That is, we are again taking alkyne. In the presence of sodium in liquid ammonia, I'm getting transalkene. How? How is that possible? So what is the difference? What's the mechanism? What are the steps involved in this one? So let me explain that. Wait for that. So same thing, we are taking alkyne. Then break the pi bond. Then how to add hydrogen? One hydrogen to this side, one hydrogen to this side. So I will get transalkene. So transalkene is formed here. So what's the reagent used? Sodium in liquid ammonia. So reagent is very important in organic chemistry, right? So let us understand the mechanism. What is happening here? So I have sodium. Sodium means it is highly electropositive in nature. So electropositive means it is ready to give electron. That means sodium gives Na plus 1 electron. So 1 electron is there. Then who will take the 1 electron? This carbon, that is sp carbon. This is also sp carbon. Okay. So initially sodium is losing 1 electron. Then second step. So Na plus is getting, we are removing Na plus. Then this carbon is taking 1 electron. 1 electron this carbon is taking. If it takes 1 electron, then total how many electrons for this carbon? Already triple bond is formed. So 6 electron for the triple bond. Then 7, 8. Then 1 electron, 9 electron. It is not possible. Only octet rule we have studied. So in order to satisfy that, we have to break one bond. Then this pi bond will be broken. Then what will happen? This carbon will take the electron. Then negative charge is formed of this carbon. Then this carbon, it has taken 1 electron from sodium. So free radical. This is free radical. Then carbon with negative charge. What is that? That is our carbanion. Oh, so if someone asks you, which are the intermediates formed here? So free radical is formed. Carbanion is also formed. So intermediate contains radical as well as carbanion. So that is formed here. So what about the next step? So sodium, it gave 1 electron. Then liquid ammonia is waiting there. So what about the liquid ammonia? So let me explain. So what's the role of liquid ammonia? So here I have CC double bond. Then some orbitals are present. Here you can see 1 unpaired electron. Then here you can see a pair of electron, that is lone pair. So what about the position? They are in opposite direction, right? Why so? It is to minimize the repulsion. So read the statement, unpaired electron of radical and lone pair of carbanion are present in lobes at anti position, opposite position. So we have to minimize the repulsion. We have to reduce the phi. Okay, then only our house will be more stable. So to minimize the repulsion, they are present in anti position. So anti position, they are present in the anti position. That is why transalkenes are formed, right? Then there is further reaction. We will study about that. But this step, free radical and carbanion and the position of electron, that is anti to each other. That is why transalkene is formed. So up to this, I hope this is clear. Free radical as well as carbanion is present. So what about the next step? So we have carbanion, we have free radical. Now comes our liquid ammonia. Ammonia is the ammonia, NH bond, 3 NH bond and lone pair is present. Then this carbanion, this minus charge, it needs some hydrogen. So it is asking this hydrogen, to come with me. Okay, that carbanion, not me. Okay. Then to go with this carbanion, this bond should be broken. This nitrogen, hydrogen, this bond should be broken. Yeah. So we can break that one. Then electrons are taken by nitrogen. So this carbanion, it is getting one H plus, right? So carbanion, one H is added to this carbon. Then what is remaining? Here one free radical, it is waiting. It is simply sitting there. It is waiting for its turn. Then again, who is coming? Sodium. Sodium is electropositive in nature. So sodium will lose electron, Na plus plus one electron. Then what will happen? This free radical, it will take one electron. So initially only unpaired electron. Now lone pair will be formed there. So two electrons are there simply sitting there. So that is known as lone pair. So that is converted to lone pair. That is negative charge. So now it is also a carbanion. Then what is the next step here? This carbanion, it will take hydrogen. From where? Again, our ammonia, NH3 is present. So this carbanion is asking this hydrogen to come with that. So what to do? We have to break this bond. Then how to break that? This nitrogen will take the electron from this bond and H plus is released. So H plus will go to carbon. Then addition of second hydrogen, that is done. Then look at the position of hydrogen. Here, hydrogen is present here. Here, hydrogen is present here. They are in opposite position. So we can call it as transalkene, right? So what is happening? Carbanion is taking hydrogen from NH3, right? So that depends the free radical and our carbanion. They are anti to the electrons are anti to each other. That is why transalkene is formed here. So this is anti addition. That last case, what is that? Syn addition. In the case of last catalyst, syn addition, same side. Here opposite side. That is why it is known as anti addition. Right? I hope this mechanism is clear to you. You have to go through this once more, then it will be pretty clear. Okay, so NH3, it is giving hydrogen H plus. Then sodium, it is giving electron. Free radical is formed, carbanion is formed. So that is the point. The liquid ammonia, sodium in liquid ammonia. What about lithium? Yeah, you can use lithium also. Lithium is also electropositive. It will give Li plus plus one electron, right? So sodium in liquid ammonia or lithium in liquid ammonia. There is a name for this one. This is reduction. This reduction is known as Birch reduction. This is known as a Birch reduction. It's a name reaction, Birch reduction. Okay, so let us try some examples, some questions. So what product will form in the addition of hydrogen to butadiene? So it is an alkyne. Addition of hydrogen to alkene, that's a reduction, right? In the presence of Lin-Last catalyst. So what is the product obtained? That is cis-alkene. Sodium in liquid ammonia. What is the product obtained? That is trans-alkene. So let us find it out. So I will give you 10 seconds to write the product. Okay, you have to answer me in the chat box. I butadiene, then hydrogen. So hydrogen is a tool. So like Rocky Bai's hammer, we have to break the pi bond and place hydrogen there. So hydrogen is our tool. Then what will happen? What will happen here? So I have butadiene. Then break the pi bond, add hydrogen to opposite side. Sorry, here it is. Last catalyst, hydrogen should be added in the same side, syn addition. Okay, then CH3 and CH3, same side. H and H, same side. What is the name? That is butadiene. Then cis-trans, it is cis-butadiene. So cis-butadiene is formed here. So what about addition of hydrogen in the presence of sodium in liquid ammonia, trans addition, right? So butyl-2 and same reactant I have sodium in NH3. We have studied the mechanism also. So what is happening here? So break the pi bond. Our tool is hydrogen. Then add hydrogen to the opposite side. Okay, so you can see CH3 and CH3 opposite side. Hydrogen and hydrogen opposite side. What is the name? Butyl-2ene. Then cis-trans, it is trans-butyl-2ene. So that is about this reaction, Lindlar's catalyst and sodium in liquid ammonia. You have to break the bond, then add hydrogen. Syn addition in one case, anti addition in another case. I hope this is clear to you. If it is clear, so let me conclude the things that we have studied. So we have studied conformers. So they have same conformational isomers, same molecular formula, but they have different spatial arrangement of atoms in the space that is different, right? The number of conformers, there are infinite number of conformers possible, but we are not studying about all these conformers. We are studying about the extreme case, that is eclipsed and the staggered conformation. So which one is more stable? That is staggered conformation. Why? Repulsion is minimum. Repulsion minimum means stability is very high. So like you and your brother, you and your sister. If you're close together, then heavy fight, right? If you're far away from each other, no tension, no strain for your mother. So that is eclipsed and staggered conformation. Then how to study this conformation? There are some representation. One is Newman's projection formula or Newman's representation. Next one is Soho's representation. We have studied that. Go to the NCERT, do some more problems. It is very important to practice more number of problems, right? Then after that, we have studied alkenes. They are also known as olefins. Why? Because they are oil forming, right? Then what is the suffix IUPAC nomenclature? We have already studied about IUPAC nomenclature. Ene is the suffix used here. Then isomerism, structural isomerism, and geometrical isomerism. Cis-trans isomers. Then trans is more symmetrical in nature. Cis is more polar in nature. We have studied about that. Then chain isomers, position isomers, we have studied. Then last, we have studied preparation of alkenes. How to prepare, which are the methods to prepare alkenes. There are a lot of methods to prepare alkenes. We will study about some of them. Then what about others? 12th, okay, 12th class, and they are told this waiting for you. You have to study. There should be something left for you to study the 12th also, right? So preparation of alkene from alkynes we have studied. So alkane plus addition of hydrogen, that is reduction. In the presence of Lindlar's catalyst, alkene is formed. Then in the presence of sodium in liquid ammonia, that is known as Birch reduction, Birch reduction. So in the case of Birch reduction, a trans-alkene is formed. So you have to remember all these things. So we have studied, we got so many new information. So what to do next? You have to revise the things. You have to recall the things. That is very, very important for you, right? So this is a homework question. So it's a very long question, right? This is also a previous year question. I've already mentioned it's very important to solve the previous year question. So read the question, go through the options, observe it carefully, then tick the correct one, right? So in the need, you have to bubble it correctly. The correct statement regarding the comparison of staggered and eclipse conformation of ethane is first option. The eclipse conformation of ethane is more stable than staggered conformation, even though eclipse conformation has torsional strain. Strain means your mother. If you're close together, there is more strain. Eclipse, you're close together, more strain for your mother. If you're far away, that is staggered conformation, less strain for your mother. So you have to select the correct answer. This is from NEET 2016. So we are doing the previous year questions along with the concept. So this is one homework question for you. Then one more very simple homework question. This was also asked in NEET. So 2-butene, right? 2-butene shows geometrical isomerism. We have studied cis-butyl-2ene, trans-butyl-2ene. So what is that? Geometrical isomerism, right? So why they are showing a geometrical isomerism? If it is a sigma bond, C sigma bond, free rotation is possible. What about pi bond? Is it possible free rotation, or is there some difficulties? So you have to find the answer. So this is all about the homework question. So we have studied ample amount of content. Recall, revise the things, do the practice. So practice makes you perfect. It's very important to practice the questions. So in the next class, we will study about the methods of preparation of alkenes. Then alkynes is waiting. Then some benzene, it is also waiting for us. So let us study it together. So today I'm ending the class. Tomorrow, next day, we will meet again. Then bye bye, students. So thank you for attending the class. We will see you in the next class. Bye bye, all the JNV students and you too, friends also. Bye bye. See you in the next class. So thank you all of you. So I'm ending it here. We will meet in the next class. Okay then. Bye bye.